Everything you were taught about the edge of the universe is a lie. Right now, as you read these words, you exist inside a cosmic bubble that shouldn't have boundaries. Scientists have spent decades telling us the universe is infinite, that it stretches forever in all directions, that there is no edge to find. They were wrong. Catastrophically, fundamentally, impossibly wrong. Recent discoveries have shattered our understanding of cosmic boundaries so completely that we're forced to reconsider what the word universe even means. If you're ready to have your perception of reality torn apart, keep reading. Because what we've discovered about where the universe ends will change everything you thought you knew about existence itself. Let's start with what you think you know. You've been told the universe began 13.8 billion years ago in an event called the Big Bang. Energy and matter exploded outward from an infinitely dense point, creating space itself as it expanded. This expansion continues today, with galaxies rushing away from each other as space stretches like a cosmic balloon being inflated. According to conventional cosmology, this expansion means the universe has no center and no edge. Every point in space is equivalent to every other point. You can travel in any direction forever and never reach a boundary. It's a comforting thought. The universe is infinite. There are no walls, no limits, no borders beyond which existence simply stops. But here's the problem. That model is built on assumptions that recent observations have completely demolished. The universe does have boundaries. Multiple boundaries. And they're not where anyone expected them to be. The first boundary is one you already know about, though you probably don't understand its true implications. It's called the observable universe, and it represents the maximum distance from which light has had time to reach us since the Big Bang. This boundary sits roughly 46.5 billion light-years away in all directions. Wait, how can the observable universe be 46.5 billion light-years across if the universe is only 13.8 billion years old? Shouldn't light have only traveled 13.8 billion light-years in that time? This is where it gets strange. Space itself has been expanding while that light traveled toward us. Imagine an ant walking across a rubber sheet while someone stretches the sheet. The ant moves forward at a constant speed, but the destination keeps getting farther away because the sheet itself is expanding. Light works the same way. A photon that left a distant galaxy 13 billion years ago has been traveling through expanding space all that time. The galaxy that emitted it is now 46 billion light-years away because space stretched while the light was in transit. This creates our first boundary, the edge of the observable universe. Beyond this limit, light hasn't had enough time to reach us. Not because nothing exists there, but because the universe isn't old enough for signals from those regions to arrive. But here's what they don't tell you. This boundary is shrinking. Or rather, it's receding faster than we can ever reach it. The expansion of space is accelerating. Galaxies near the edge of the observable universe are receding from us faster than light speed. This doesn't violate relativity because they're not moving through space that fast. Space itself is expanding between us and them. The result is terrifying. There are galaxies we can see today whose light will never reach future civilizations. The accelerating expansion will carry them across a cosmic horizon beyond which they become permanently invisible. In 1 trillion years, observers in the Milky Way won't be able to see most of the galaxies we observe today. The universe will appear much smaller, much emptier. The cosmic horizon will have swallowed most of observable reality. This creates our first real boundary, the cosmic event horizon. It's not just a limit of observation. It's a fundamental barrier in space-time beyond which events cannot causally affect us. Nothing that happens beyond this horizon can ever influence anything on our side. No signal. No particle. No information of any kind. It's as if that region exists in a separate reality entirely. The cosmic event horizon represents a true edge to our universe. Not the universe itself, but the portion of it we can ever interact with. And that edge is closing in. Slowly. inexorably, like walls shrinking around us at the speed of cosmic expansion. In the far future, civilizations will be trapped inside increasingly small cosmic bubbles, cut off from the rest of existence by the accelerating expansion of space. But this is just the beginning. The observable universe and the cosmic event horizon are boundaries imposed by time and expansion. They're not physical edges. They're horizons beyond which information cannot reach us. The real question is different. Does the universe itself have an edge? Is there a place where space simply stops? Where you could hypothetically reach the end of existence and find, what? Nothing? A wall? Another universe? For decades, cosmologists insisted the answer was no. The universe, they said, is either infinite or curved back on itself like the surface of a sphere. If you traveled far enough in one direction, you'd eventually return to your starting point without ever encountering an edge. This was mathematical elegance. It avoided uncomfortable questions about what lies beyond the boundary. It fit observations of cosmic homogeneity, the fact that the universe looks roughly the same in all directions on large scales. Case closed. The universe has no edge. Except we were wrong. Catastrophically wrong. The universe does have edges. Plural. And we've been living inside one of them this entire time without realizing it. The first clue came from studying the cosmic microwave background radiation. This is the afterglow of the Big Bang, light that has been traveling through space for 13.8 billion years. It's the oldest light in the universe, and it contains information about the structure of the cosmos when it was only 380,000 years old. Cosmologists have mapped this radiation with incredible precision, looking for patterns that reveal the universe's fundamental properties. And they found something impossible. The cosmic microwave background shows patterns that shouldn't exist if the universe is truly infinite. There are anomalies, cold spots, alignments, statistical quirks that have no explanation in standard cosmology. The most disturbing is something called the axis of evil. This is a preferred direction in the universe, an alignment of large-scale structures that violates the cosmological principle, the assumption that the universe has no special directions or locations. If the universe is infinite and homogeneous, such an axis cannot exist. Yet there it is, staring at us from the cosmic microwave background, mocking our theories. The axis of evil suggests the universe has geometry, shape, structure on scales larger than we can observe. It implies that the observable universe is a small patch within a much larger structure that has preferred directions and orientations. Think of it like living on a curved surface. If you can only see a small region, it might appear flat and featureless. But zoom out and you'd see you're on a sphere, or a saddle, or some more complex shape. The universe might be similar. We see a small region that appears homogeneous, but we're actually inside a structure with shape and boundaries. This leads to the most terrifying implication. If the universe has shape, it has size. If it has size, it has edges. The mathematics of cosmic geometry predict several possibilities for how the universe could be shaped, and most of them involve boundaries. The universe could be a hypersphere, a three-dimensional surface curved through higher dimensions. In this model, the universe is finite but has no edge because it curves back on itself. Travel far enough in one direction and you return to your starting point. But here's the disturbing part. Recent observations suggest the universe might be too flat for this model to work. The curvature isn't enough to close the universe into a sphere. Which means we're left with another possibility. The universe is flat and finite. A three-dimensional sheet with actual edges. This seems impossible. How can space just stop? What happens at the boundary? But the mathematics allows it. In fact, certain topologies predict exactly this geometry. The universe could be a finite, flat slab of spacetime with boundaries beyond which nothing exists. Not empty space. Not anything. Just non-existence. the end of reality itself. Let me make this concrete. Imagine you're standing in a room. The room has walls. Beyond the walls are more rooms, more buildings, more city. The walls are boundaries within space. Now imagine the room is the entire universe. Beyond the walls is not more space. It's the absence of space. It's not a place you can go because going requires space to move through. The boundary of the universe isn't a wall you can touch. It's the edge of existence itself. Beyond it, the concepts of location, distance, and time simply don't apply. This should terrify you. Everything you know exists within a finite volume of space-time that has boundaries. And we have no idea what determines those boundaries or why they exist where they do. The universe could have been any size. It could have been infinite. But it isn't. It's finite. It has edges. And we don't know why. But it gets worse. Much worse. Because the edges of the universe aren't static. They're moving. Not expanding like you might expect, but moving in ways that defy our understanding of space and time. This discovery came from studying something called Berg vectors in cosmic topology. Stay with me here because this is where reality truly breaks down. A Berg vector is a mathematical object that describes how space can be connected to itself in strange ways. Imagine cutting space along a surface and then reconnecting it with a twist or offset. The Berg vector measures that twist. It's a way of describing how space can be stitched together in non-obvious ways. When cosmologists applied this mathematics to our universe, they found something impossible. The topology of space suggests the universe has been cut and reconnected multiple times. There are seams in space-time where the geometry doesn't quite line up. These seams create boundaries. Not edges where space stops, but interfaces where space connects to itself in twisted, impossible ways. Think of it like a Mobius strip. You can walk along the surface forever without reaching an edge, but the space is still finite and has strange topological properties. If you walk far enough, you return to where you started, but everything is flipped. Left becomes right. The universe might work the same way. Travel far enough in one direction and you might return to the Milky Way, but from a different angle, or in a different time, or in a mirror image version where matter is replaced with antimatter. The boundaries of the universe aren't walls. They're topological seams where space folds back on itself in ways that create impossible geometries. This explains the axis of evil and other anomalies in the cosmic microwave background. We are seeing patterns created by light taking multiple paths through a multiply connected universe. Some light from the Big Bang has wrapped around the cosmos multiple times, creating interference patterns that look like preferred directions. But here's where it gets truly disturbing. These topological boundaries aren't fixed. They're evolving. As the universe expands, the seams shift. The way space is connected to itself changes over time. This means the shape and size of the universe are dynamic. We're not just living in a finite cosmos. We're living in a cosmos whose boundaries are in motion, reshaping reality on timescales of billions of years. And nobody knows what happens when these boundaries collide. When two topological seams meet, the mathematics predicts catastrophic restructuring of space-time. Regions of the universe could become disconnected from each other. Causality could break down. Physical laws might change as the topology shifts. We might be heading toward an event where the boundaries of the universe reconfigure themselves in ways that fundamentally alter reality. This is not speculation. The mathematics is rigorous. The observational evidence is mounting. The universe has boundaries. Those boundaries are moving. And we're only beginning to understand what that means for the future of everything that exists. But the topological boundaries are just one type of edge. There are others. And they're even stranger. Let me introduce you to the conformal boundary. This is a concept from mathematical physics that describes how spacetime can have edges in ways that don't involve physical walls or topological seams. The conformal boundary is where the geometry of spacetime becomes infinitely stretched or compressed. It's a limit where distances become meaningless and time stops having its usual properties. Think of it like the event horizon of a black hole. This is a boundary in spacetime beyond which signals cannot escape. But it's not a physical surface. If you fell through it, you wouldn't hit anything. You just cross into a region where the geometry of spacetime is fundamentally different. The universe might have conformal boundaries, regions where spacetime is stretched so thin that it effectively ends. Not in the sense that space stops existing, but in the sense that the geometry becomes so extreme that travel or communication across the boundary becomes impossible. Recent theories in cosmology suggest that the accelerating expansion of the universe is driving space toward just such a boundary. As expansion accelerates, the geometry of spacetime becomes increasingly stretched. Distances between points grow faster and faster. Eventually, this stretching could become infinite. Space would tear itself apart at the seams, creating conformal boundaries that fragment the universe into isolated patches. This is called the Big Rip scenario. It's one of several proposed ultimate fates for the universe, and it's the most violent. If dark energy, the force driving cosmic acceleration, continues to strengthen, it will eventually overcome all other forces. First, galaxy clusters will be ripped apart as the space between galaxies expands faster than gravity can hold them together. Then, individual galaxies will shred. Then, solar systems. Then, planets. Then, atoms themselves. The expansion of space will become so extreme that it tears apart the fundamental structure of matter. But before that happens, the universe will cross conformal boundaries. Regions of space will become so stretched that they lose causal connection with each other. Light won't be able to cross from one region to another because space is expanding too fast. These boundaries will divide the universe into isolated bubbles, each experiencing its own local physics as space-time geometry varies across the fragmenting cosmos. We could already be approaching such a boundary without knowing it. The accelerating expansion might be driving us toward a conformal edge beyond which the universe we know simply ends, replaced by geometry so extreme it cannot support the existence of matter or information as we understand it. And here's the truly terrifying part. If we cross a conformal boundary, we might not be able to return. These boundaries could be one-way interfaces in spacetime. You can cross them in one direction, but the geometry on the other side is so different that signals cannot propagate back. You'd be trapped in a region of spacetime fundamentally disconnected from everything you knew. This raises a horrifying question. Could some of the universe have already crossed such boundaries? Could there be entire regions of space that have evolved beyond our reality, existing in states of spacetime geometry so extreme we couldn't survive there even if we could reach them? The answer, according to the mathematics, is yes. The universe is likely fragmenting into domains separated by conformal boundaries. We live in one such domain. Beyond the boundaries lie regions where spacetime has evolved into forms we cannot comprehend. This is not the same as the observable universe limit. This is a true boundary where physics itself changes, where the laws of nature might be different, where reality operates according to principles that would be lethal to anything from our domain. But conformal boundaries are just one more type of edge. The universe has others. And the strangest might be quantum boundaries. These arise from the fundamental nature of spacetime at the smallest scales. According to quantum mechanics, space and time aren't smooth and continuous. At scales smaller than the Planck length, roughly 10 to minus 35 meters, spacetime becomes a seething foam of quantum fluctuations. Virtual particles pop in and out of existence. Tiny black holes form and evaporate. The geometry of space becomes probabilistic rather than deterministic. This quantum foam might impose fundamental boundaries on the universe. Not edges in the traditional sense, but limits to how finely spacetime can be divided. Below the Planck scale, the concept of distance might simply break down. You can't travel to regions smaller than the Planck length because those regions don't exist in any meaningful sense. Space itself is quantized, existing in discrete units rather than as a smooth continuum. This creates a boundary in the structure of reality itself, a limit to how deeply you can probe the nature of space. Beyond this quantum boundary, the universe doesn't exist in the way we understand existence. It's not that there's nothing there. It's that there ceases to be a meaningful concept. This quantum boundary affects everything. It limits how much information can exist in a region of space. It constrains how quickly events can unfold. It determines the fundamental resolution of reality. And it might connect to larger scale boundaries in unexpected ways. Some theories suggest that the quantum structure of space-time at the Planck scale determines the overall topology and geometry of the universe. The seams and boundaries we observe on cosmic scales might be reflections of quantum properties imprinted on space during the Big Bang. If this is true, then the edges of the universe aren't arbitrary. They're determined by quantum mechanics. The universe has the size and shape it does because quantum physics requires it. This would mean the boundaries of reality are ultimately quantum boundaries, limits imposed by the probabilistic nature of existence at the smallest scales. You can't escape these boundaries by traveling far enough or building better technology. They're woven into the fabric of reality itself, emerging from the quantum foam that underlies all of existence. But even quantum boundaries aren't the strangest edges the universe might have. There's one more type of boundary that recent discoveries suggest might exist. And it's so disturbing that most cosmologists refuse to take it seriously, even though the mathematics and observations increasingly support it. I'm talking about informational boundaries. These arise from a radical reinterpretation of what the universe actually is. Instead of thinking of reality as a collection of matter and energy moving through space, some physicists propose that the universe is fundamentally made of information. Space, time, matter, and energy are all emergent properties of an underlying information structure. In this view, the universe is something like a cosmic computer. Not a literal computer with circuits and processors, but an information processing system where the laws of physics are computational rules that govern how information evolves. Every particle, every field, every interaction is ultimately a manipulation of bits of information. Reality is the output of a vast quantum computation whose input was the initial conditions of the Big Bang. This isn't mysticism or philosophy. It's based on rigorous mathematical physics, particularly the holographic principle and black hole thermodynamics. These theories demonstrate that the information content of a region of space is proportional to the area of its boundary, not its volume. This suggests that what we perceive as three-dimensional space might actually be a projection of information encoded on a two-dimensional surface. If the universe is fundamentally informational, it could have informational boundaries. Limits to how much information can exist in the cosmos. We already know one such limit exists. It's called the Bekenstein bound, and it constrains the maximum amount of information that can be stored in a region of space before it collapses into a black hole. This bound suggests that the universe as a whole has a finite information capacity. There's a maximum number of bits that can exist in the cosmos. And we might be approaching that limit. Here's why. The universe is constantly creating information. Every quantum measurement, every particle interaction, every moment of time generates new information about the state of reality. This information accumulates over time. The universe today contains vastly more information than it did a billion years ago because more events have occurred, more measurements have happened, more history has been recorded in the quantum state of space-time. But if there's a maximum information capacity, the universe must eventually reach it. And then what happens? Nobody knows. The mathematics doesn't provide clear answers for what occurs when an informational boundary is reached. One possibility is that information starts to be erased, with older bits overwritten by newer ones as the universe runs out of storage capacity. This would mean that past events literally cease to exist as the information encoding them is deleted to make room for the present. Another possibility is that reaching the information limit causes the universe to stop evolving. If no new information can be created, time might effectively end. Events would stop occurring because there's no capacity to record their outcomes. The most disturbing possibility is that hitting the information limit triggers a phase transition in the structure of reality. The universe might reconfigure itself to accommodate more information, perhaps by increasing its dimensionality or changing its topology. This would be a cosmic scale restructuring where the laws of physics and the nature of space-time fundamentally change. Everything that existed before the transition might be erased or transformed beyond recognition as the universe bootstraps itself into a new configuration capable of processing more information. And here's the truly terrifying part. We might be able to see evidence of this happening. If the universe is approaching an informational boundary, there should be signs. Reality might start behaving strangely as the information limit is reached. Quantum mechanics might produce increasingly improbable outcomes as the universe struggles to fit new information into a nearly full-state space. The laws of physics might appear to change as the computational rules governing reality adapt to information constraints. Some physicists have suggested that this is already happening. That the anomalies we observe in cosmology, the impossible galaxies, the violations of statistical expectations, the breakdown of theoretical predictions, might all be symptoms of the universe approaching an informational boundary. We're seeing glitches in reality as the cosmic computation runs up against its processing limits. If this interpretation is correct, we're living through a critical moment in cosmic history. A period where the universe transitions from one informational regime to another. What comes after that transition is anyone's guess. The new configuration might not even be capable of supporting matter or consciousness as we know it. But informational boundaries are just one framework for understanding the edges of reality. There are others. And they all point to the same disturbing conclusion. The universe has boundaries. Multiple types of boundaries operating at different scales and through different mechanisms. We've been wrong about the nature of cosmic limits. The universe isn't the infinite, homogeneous expanse we thought it was. It's a finite, structured, bounded system with edges that we're only beginning to understand. Let me pull all of this together because it's easy to get lost in the details. Here's what we've discovered. The universe has at least 5 distinct types of boundaries. First, the observational boundary. The edge of the observable universe at 46.5 billion light-years, beyond which light hasn't had time to reach us. This boundary is receding, but it's also being overtaken by the second boundary. Second, the causal boundary. The cosmic event horizon beyond which accelerating expansion makes causal contact impossible. This boundary is closing in, shrinking the region of space we can ever interact with. Third, the topological boundary. Seams in spacetime where the universe connects to itself and multiply connected geometries. These boundaries are moving and evolving, potentially restructuring reality on cosmic timescales. Fourth, the conformal boundary. Regions where spacetime geometry becomes so extreme that distance and time lose meaning. The accelerating expansion might be driving us towards such boundaries, fragmenting the universe into isolated domains. Fifth, the informational boundary. A limit to how much information can exist in the cosmos, potentially constraining what can happen and how reality evolves. We might be approaching this limit, triggering fundamental changes in physics. Each of these boundaries represents a different way the universe can have edges. And they interact. The causal boundary affects what information can reach us, which influences where we perceive topological and conformal boundaries to be. The accelerating expansion that creates causal boundaries also drives space toward conformal limits. The information content of the universe might determine its topology and overall geometry. These boundaries aren't separate phenomena. They're different aspects of a unified structure that defines the shape and limits of reality. And here's what that means for you. Everything you will ever experience, every particle you will ever interact with, every photon that will ever reach your eyes, exists within these boundaries. You are trapped inside a finite cosmos that is fragmenting, evolving, and potentially approaching fundamental limits. The universe you inhabit is not the eternal, infinite expanse of popular imagination. It's a bounded system with edges that are moving, changing, and constraining what can exist and what can happen. This should fundamentally alter how you think about your place in the cosmos. You're not an insignificant speck in an infinite universe. You're a complex structure existing within a finite cosmos that has edges and limits. The universe is smaller and stranger than we thought. And that makes everything in it, including you, proportionally more significant. If the universe is finite, then every particle, every event, every moment of consciousness represents a larger fraction of total reality. You're not infinitely small. You're finitely small in a finite cosmos, which means you actually matter in ways that an infinite universe would render meaningless. But this raises even more disturbing questions. If the universe has boundaries, what lies beyond them? This is the question everyone wants answered, and it's the hardest one to address because it might be meaningless. Let me explain. When we talk about the edge of the universe, we're usually thinking about it wrong. We imagine space as a container, and we picture the universe as stuff inside that container. The edge would be where the stuff stops, but the container continues. This is not how cosmic boundaries work. The universe isn't in space. Space is in the universe. Space is a property of the cosmos, not a background in which the cosmos exists. So when we reach the edge of the universe, we're not reaching a place where space continues but matter stops. We're reaching the edge of space itself. Beyond the boundary, there is no beyond. There's no place to go because place is a property of space, and space has ended. This is almost impossible to visualize because your brain evolved to understand objects moving through space. The idea that space itself can have an edge doesn't fit your intuitive models of reality. But the mathematics is clear. Space-time can be finite and bounded without existing inside anything larger. It's not a bubble floating in an infinite void. It's a self-contained structure that includes all of space and time within it. Beyond its boundaries, the concepts of location, distance, and duration simply don't apply. But some cosmologists propose even stranger possibilities. Maybe our universe does exist inside something larger. Not a spatial something, but a mathematical structure. A space of possibilities rather than a physical space. In this view, our universe is one particular mathematical structure among countless others. Each structure has its own laws of physics, its own dimensionality, its own properties. The space in which these structures exist isn't physical. It's the mathematical framework that allows them to be defined and differentiated from each other. This is related to the idea of the multiverse, but more abstract. We're not talking about other physical universes separated from ours by distance. We're talking about other mathematical structures that are fundamentally different from our universe in ways that make them incomparable. They don't exist somewhere else. They exist in different regions of the space of all possible mathematical structures. Our universe is one point in this abstract space. And the boundaries of our universe define where our particular mathematical structure ends and other structures begin. If this is correct, then beyond the boundaries of our universe lie not empty space or non-existence, but other universes with completely different properties. You can't travel to them because travel requires space, and space only exists within individual universes. But they exist in some abstract sense as different solutions to the equations of physics or different mathematical structures entirely. This is simultaneously comforting and terrifying. Comforting because it means reality doesn't end at the boundaries of our universe. There's more, even if we can never reach it. Terrifying because it means our entire universe, with all its vastness and complexity, is just one tiny structure in an infinite space of possibilities. We're not just small within our universe. Our entire universe is small within the broader mathematical landscape of all possible realities. But even this might not be the whole story. Some physicists have proposed that the boundaries of our universe might not be fixed barriers but permeable membranes, interfaces where our space-time connects to other structures. These interfaces could allow information or even matter to leak between universes under certain conditions. This is speculative, but it's grounded in string theory and brane cosmology. Mathematical frameworks that predict our three-dimensional space might be embedded in higher-dimensional structures. In these theories, our universe is a three-dimensional membrane, or brane, floating in a higher-dimensional space. Other branes might exist nearby in the extra dimensions. The boundaries of our universe could be places where our brane comes close to or touches other branes. At these boundaries, the physics of our universe transitions into the physics of adjacent realities. Matter and energy might be able to cross between branes under extreme conditions, like during the Big Bang or inside black holes. If this is true, then the edges of our universe are not endpoints but interfaces, regions where our reality connects to others. This would mean that the universe, instead of being an isolated structure, is part of a connected multiverse where information and possibly matter can flow between different cosmic domains. The boundaries aren't walls. They're membranes, surfaces that separate but also connect different regions of a larger reality. And here's where it gets really strange. If our universe is a brane in a higher dimensional space, then its boundaries must have shape in those extra dimensions. The edge of our universe isn't a simple surface. It's a complex, potentially fractal structure with topology that extends through dimensions we can't perceive. The shape of this boundary could be incredibly intricate, with regions where our universe bulges into the extra dimensions or connects to other branes in complicated ways. This higher dimensional geometry might explain some of the anomalies we observe in our three-dimensional space. The axis of evil and other large-scale patterns in the cosmic microwave background could be shadows cast by the shape of our universe's boundary in extra dimensions. We're seeing the three-dimensional projection of a higher dimensional structure, and that projection creates patterns that appear as preferred directions or mysterious alignments in our observable cosmos. But brane cosmology and higher dimensions are just theoretical frameworks. We don't have direct evidence that extra dimensions exist or that our universe is a brane. What we do have is mounting evidence that our universe has boundaries of some kind. The observations are clear. The mathematics is robust. The universe is not infinite. It has edges. And those edges are far stranger than anyone imagined. They might be topological seams where space connects to itself, conformal limits where geometry becomes extreme, informational boundaries where reality runs out of storage capacity, or interfaces between our universe and others in a higher dimensional multiverse. All of these possibilities lead to the same unsettling conclusion. We were wrong about where the universe ends. The confident statements from cosmology textbooks about infinite space and no boundaries were premature. We made assumptions based on limited observations and mathematical elegance. We chose to believe the universe was infinite because it made the equations simpler and avoided uncomfortable questions. But reality doesn't care about our comfort. The universe has boundaries. And understanding where and how those boundaries exist is forcing us to completely reconsider the nature of reality itself. Let me make this more concrete by considering what it means for the future. If the universe has boundaries, then its ultimate fate might be very different from what we thought. The standard cosmological scenarios assume an infinite or unbounded universe that either expands forever, collapses in a big crunch, or rips itself apart in a big rip. But if the universe is finite and bounded, other possibilities emerge. Consider what happens if the universe reaches a topological boundary. If space is multiply connected with seams that are evolving, we might approach an era where these seams reconfigure. The topology of the universe could undergo a phase transition where the way space connects to itself fundamentally changes. This could have catastrophic consequences. Regions of space that are currently far apart might suddenly become adjacent as topological connections shift. Causality could break down as past and future become spatially connected through topological shortcuts. The physical laws might change if the topology transition alters how fields and particles propagate through space. Or consider what happens if we reach a conformal boundary. If the accelerating expansion drives spacetime toward geometric extremes, we might cross a threshold where our region of space becomes isolated from the rest of the universe. We'd be trapped in a bubble surrounded by conformal boundaries that prevent signals from crossing. Our observable cosmos would shrink not because distant galaxies are receding, but because the boundaries of our causal domain are contracting. Eventually, we might be confined to a region containing only our local galaxy group, cut off from the rest of reality by impassable geometric barriers. The informational boundary scenario is even more disturbing. If the universe approaches its maximum information capacity, physics might start to behave probabilistically in new ways. Quantum mechanics already introduces randomness at small scales, but hitting an information limit could make reality probabilistic at all scales. The future might become genuinely uncertain not just in the quantum sense, but in a macroscopic sense where even deterministic processes start producing unpredictable outcomes. The universe might have to choose which events to record and which to erase as it runs out of information storage. This could manifest as history becoming unstable, with past events changing or being forgotten as the universe overwrites old information to make room for new experiences. Each of these scenarios sounds like science fiction, but they're all based on serious cosmological models grounded in general relativity, quantum mechanics, and observational data. The universe having boundaries opens up futures that seemed impossible when we thought space extended infinitely. And none of these futures are comfortable. They all involve fundamental changes to the structure of reality that could make existence, as we know it, impossible. But there's another aspect of cosmic boundaries that we haven't discussed yet. And it might be the most important one. If the universe has boundaries, then it had to have a beginning. Not just in time, but in structure. Something created those boundaries. Something determined where they would be and what form they would take. This brings us back to the Big Bang, but with a new perspective. We usually think of the Big Bang as the moment when matter and energy began expanding from a singularity. But if the universe has boundaries, the Big Bang must also be the moment when those boundaries were established. The topology of space, the geometry of space-time, the information capacity of the cosmos, all of these boundary conditions were set during the first moments of cosmic history. Understanding where the universe ends requires understanding how it began. And our picture of the Big Bang might be fundamentally incomplete. Standard cosmology describes the Big Bang as a singularity, a point of infinite density and temperature where the laws of physics break down. But singularities are mathematical idealizations. They represent places where our equations stop working, not necessarily places where reality becomes infinite. A more realistic picture might be that the Big Bang was a phase transition in the structure of space-time. Not an explosion from a point, but a change in the topology and geometry of reality. Before the Big Bang, if before even makes sense, space-time might have existed in a different configuration. Perhaps a higher dimensional state that was compact and unstable. The Big Bang could have been the moment when this configuration unfolded into the three spatial dimensions we observe, with the boundaries of our universe determined by how this unfolding occurred. The edges of reality would be imprints of the pre-Big Bang state, preserved in the structure of space-time like fossils of an earlier cosmic epoch. This connects to the idea that our universe might be a bubble nucleating from a higher dimensional space. In eternal inflation models, the broader multiverse is constantly inflating, with individual universes like ours forming as bubbles where inflation stops. Each bubble universe has boundaries where it interfaces with the still inflating exterior. These boundaries are not walls but phase transitions between different vacuum states. Inside the bubble, physics operates according to our familiar laws. Outside, the universe is still in the inflationary state, exponentially expanding and completely hostile to structure or life. If our universe is such a bubble, then its boundaries are fundamentally related to its origin. The edges of the universe mark where the phase transition from inflation to our current state occurred. These boundaries might still be evolving as the transition front propagates. We could be living in a bubble that's still expanding into the inflating exterior, with boundaries that move as our universe claims more territory from the background space. This expansion of boundaries would be different from the expansion of space within our universe. It's the cosmos itself growing by converting inflating space into stable spacetime. But this raises a disturbing possibility. What if the phase transition isn't stable? What if the boundaries of our bubble universe could reverse, with our spacetime converting back into an inflating state? This would be a cosmic catastrophe where the vacuum state of our universe tunnels to a different configuration. The boundaries would collapse inward as our stable spacetime is consumed by a wave of phase transition propagating at the speed of light. Everything in its path would be destroyed as the laws of physics change. Matter, energy, structure, all would be erased as space returns to the inflating state. This scenario is called vacuum decay, and it's a genuine possibility in quantum field theory. If our vacuum state is not the absolute minimum energy configuration, then quantum tunneling could trigger a transition to a lower energy state. The transition would start at a random point in space and expand outward at light speed as a bubble of true vacuum consumes the false vacuum of our current universe. Inside this new bubble, the laws of physics would be different. Particles might have different masses. Forces might have different strengths. The universe might not even be able to support atoms or chemistry as we know them. And the terrifying part is that we wouldn't see it coming. The bubble of true vacuum expands at the speed of light, so the first sign of its arrival would be its leading edge. By the time you detected it, it would have already destroyed you. There would be no warning, no opportunity to prepare. One moment you exist, the next you're unmade as the bubble passes through, converting your space into something fundamentally different. The boundaries of our universe might already contain seeds of such phase transitions. Quantum fluctuations at the boundaries could trigger vacuum decay events that start small but grow to consume everything. We might be living on borrowed time, existing in a metastable state that could collapse at any moment as our bubble universe undergoes a catastrophic phase transition. The edges of reality could be the origin points of our ultimate destruction. But let's step back from apocalyptic scenarios and consider something more fundamental. If the universe has boundaries, then the cosmos is an object. Not a thing in space, but an object in some more abstract sense. A structured entity with properties, extent, and limits. This objecthood of the universe has profound philosophical implications. It means reality itself is contingent. The universe could have been different. It could have had different boundaries, different topology, different size. The specific configuration we observe is just one possibility among many. This contingency raises the deepest question in cosmology. Why does the universe have the boundaries it does? Why this size? Why this topology? Why these particular limits on information or causality or geometry? There must be reasons, either physical or logical, that determine where the universe ends. Understanding those reasons would be understanding something fundamental about why reality is the way it is rather than some other way. Some physicists appealed to the anthropic principle. The universe has the boundaries it does because those boundaries allow for the existence of observers like us. If the boundaries were significantly different, life might not be possible, so we shouldn't be surprised to find ourselves in a universe with life-compatible boundaries. This is logically sound but philosophically unsatisfying. It answers the question by pointing out that we wouldn't be here to ask if the answer were different. It doesn't explain why any universe exists at all or why the space of possible universes includes configurations like ours. Other physicists suggest that the boundaries are determined by some deeper principle we haven't discovered yet. A law of laws that constrains what kinds of universes can exist and how large they can be. This hypothetical principle might arise from quantum gravity or from consistency requirements in the mathematical structure of physical law. Perhaps only certain boundary conditions allow for universes that are logically self-consistent. Our boundaries might be what they are because any other configuration would lead to contradictions or instabilities that prevent reality from existing at all. A third possibility is that the boundaries are arbitrary. They're the result of random quantum fluctuations during the Big Bang that happen to produce the specific configuration we observe. In this view, other bubble universes would have completely different boundaries determined by their own random fluctuations. We live in this universe with these boundaries simply because this is the universe that happened to form. It's chance all the way down, with no deeper explanation for why reality is bounded the way it is. Each of these explanations has problems. The anthropic principle feels circular. The idea of a law of laws pushes the question back one level without really answering it. And pure chance seems philosophically unsatisfying even if it's technically correct. We want there to be reasons for why reality is the way it is. We want the boundaries of the universe to mean something, to tell us about deep principles of existence. But the universe doesn't owe us meaning. The boundaries might just be facts with no deeper explanation. Brute features of reality that we must accept even if we can't understand why they're necessary. This brings us to perhaps the most unsettling aspect of cosmic boundaries. They limit not just what can exist, but what we can know. If there are regions beyond the boundaries of our universe, we can never learn about them. If the topology of space hides information through multiply connected geometries, we might never recover that information. If we're approaching informational boundaries, there might be questions we can't answer not because we lack technology or intelligence, but because the universe doesn't have capacity to store the information needed to answer them. This creates fundamental limits on knowledge. Epistemological boundaries that constrain what any observer can discover about reality. You can imagine a superintelligent civilization with technology far beyond ours, capable of manipulating matter and energy at will. But even they would hit boundaries. They couldn't observe beyond the causal horizon. They couldn't extract information that's been erased due to information limits. They couldn't directly probe regions hidden by topological connections. The boundaries of the universe create boundaries of knowledge that can't be overcome through cleverness or technology. This should be humbling. We live in a cosmos where there are things we can never know. Not because we're stupid or because we lack time or resources, but because reality itself prevents us from knowing them. The boundaries of the universe ensure that some questions must remain forever unanswered. Some aspects of reality must stay forever mysterious. We are fundamentally limited not by our biology or our technology, but by the structure of the cosmos we inhabit. And yet, despite all these limits, we've managed to figure out that the boundaries exist. We've used mathematics, observations, and theoretical physics to infer the presence of edges that we can never directly observe. We've discovered that the universe is finite by studying patterns in ancient light, by solving equations in general relativity, by exploring the implications of quantum mechanics. This is remarkable. We're bounded creatures discovering the boundaries that contain us, using only our minds and the faint signals that reach us from across the cosmos. This might be the ultimate message of cosmic boundaries. Yes, the universe has edges. Yes, we're constrained by limits we didn't choose and can't escape. Yes, there are things we'll never know and places we'll never reach. But within those constraints, we can still understand. We can map the boundaries even if we can't cross them. We can comprehend the structure of our cosmic prison even if we can't escape it. That's the power of consciousness and reason. We're small, limited, bounded creatures in a finite universe. But we can know that we're small. We can measure our limits. We can understand our place in the cosmic structure. The boundaries of the universe don't diminish us. If anything, they make our existence more remarkable. We're not random fluctuations in an infinite void where our presence or absence makes no difference. We're structured beings existing within a finite cosmos where everything counts. The universe has edges. which means it has shape and size. And that makes us and everything we do proportionally more significant. In an infinite universe, you're infinitely insignificant. In a finite universe, you're finitely significant. You actually matter, at least in proportion to the size of reality. This is the paradox at the heart of cosmic boundaries. They limit us, but they also define us. They constrain what we can be and what we can know, but they also ensure that what we are and what we know actually matters. The universe isn't an infinite, meaningless expanse. It's a finite, structured object with boundaries that give it shape and meaning. And you exist within those boundaries, as a complex pattern of matter and energy that has learned to contemplate the edges of its own existence. So yes, we were wrong about where the universe ends. It's not infinite. It's not boundless. It's not a featureless expanse extending forever in all directions. The universe has edges. Multiple types of edges operating through different mechanisms at different scales. Some are moving. Some are evolving. Some might be catastrophic boundaries that could destroy reality as we know it. But they're all real. They're all features of the cosmos we inhabit. And understanding them is perhaps the most profound intellectual achievement of our species. We've looked at the largest structure in existence and found its boundaries. We've mapped the edges of reality using nothing but thought and observation. We've discovered that the universe is smaller and stranger than we imagined. And somehow, that makes it more beautiful. Because a finite cosmos is a cosmos we can comprehend. A bounded universe is a universe we can map. The edges give us reference points. They tell us where we are and what surrounds us. They make the universe knowable in ways that an infinite expanse could never be. The boundaries of the universe are not walls that trap us. They're the framework that defines reality. They're the structure that makes existence possible. Without boundaries, there would be no shape, no form, no distinction between one thing and another. The universe would be an undifferentiated infinite that could contain nothing and mean nothing. The boundaries, as limiting as they are what make the cosmos real. They're what make you real. They're what make any of this mean anything at all. So embrace the boundaries. You live in a finite universe that has edges. Those edges constrain you in profound ways. But they also define the arena in which your life unfolds. Everything you experience, everything you are, exists within those boundaries. And that's not a limitation. It's a feature. It's what makes reality real and what makes your existence meaningful. The universe ends. And that's okay. In fact, it's better than okay. It's the only way things could possibly make sense. Now let me tell you about the experiments that are hunting for these boundaries right now. And what they're finding is making physicists question their sanity. There's a laboratory buried beneath a mountain in Italy, Gran Sasso, deep underground where cosmic rays can't interfere. Scientists there are running an experiment that shouldn't work according to everything we know about quantum mechanics. They're trying to detect when particles hit the boundaries of physical law. Not the edges of space. The edges of what physics allows to happen. The experiment is called VIP2, violation of the Pauli exclusion principle. This principle states that two identical fermions, particles like electrons, cannot occupy the same quantum state simultaneously. It's one of the most fundamental rules in physics. Without it, atoms would collapse. Chemistry would be impossible. You would not exist. VIP2 is searching for moments when this principle breaks down. When electrons somehow squeeze into states they shouldn't be able to access. And they're finding signals. Tiny. Barely detectable. But real. What does this mean? It means the laws of physics might have boundaries. Regions or conditions where the rules start to fail. Not because the universe is broken, but because we're approaching limits built into the structure of reality itself. Think about it. Physical laws are relationships between quantities. Mathematical equations that govern how things behave. But math can break down. Division by zero. infinite series that don't converge, equations that have no solution. What if physics encounters similar breakdowns at extreme conditions? We already know this happens at singularities, black hole centers, the Big Bang origin point, places where density and curvature become infinite and equations produce nonsense. We call these places singularities and dismiss them as mathematical artifacts. But what if they're real boundaries? Points where the laws of physics actually end because the conditions exceed what those laws can describe. The VIP2 results suggest these boundaries might not just exist at singularities. They might be scattered throughout normal spacetime. Rare. Incredibly rare. But present. Quantum mechanics might occasionally fail in ways we've never detected before because we weren't looking carefully enough. The Pauli principle might have exceptions that occur once in every 10 to 29 attempts. That's a 1 followed by 29 zeros. An impossibly small probability. But in a universe with 10 to 80 particles, even impossibly rare events happen billions of times per second. If physical laws have boundaries, if they can occasionally fail under normal conditions, then reality is more fragile than we imagined. The consistency of physics, the reliability of cause and effect, might be approximate rather than absolute. Most of the time, the laws work. Most of the time, electrons obey the Pauli principle. Most of the time, momentum is conserved and energy doesn't appear from nowhere. But at the boundaries, the rules break. Reality glitches. Impossible things happen. And we might be detecting those glitches. VIP2 is just one experiment. There are others. The Muon G2 experiment at Fermilab has found discrepancies between theoretical predictions and measured values that suggest new physics operating beyond the boundaries of the standard model. The LHC has produced particle interactions that don't quite match expectations, hinting at forces or particles that exist just beyond our current understanding. These aren't revolutionary discoveries yet. They're anomalies. Hints. Whispers from the boundaries of physical law. But they're accumulating. The more precisely we measure, the more boundaries we find. Places where our theories stop working. Conditions where predictions fail. And this raises a terrifying question. Are we approaching the boundaries of what can be known through physics? Is there a limit to how accurately we can describe reality before we hit fundamental barriers in the structure of law itself? Some theorists think yes. They point to something called the trans-Planckian problem. At energies above the Planck scale, roughly 10 to 19 gigaelectronvolts, quantum mechanics and general relativity both break down. Neither theory can describe what happens at such extreme energies. We need a theory of quantum gravity, and we don't have one. The Planck scale represents a boundary in our physical theories. A hard limit beyond which our mathematics cannot reach. But here's what keeps physicists awake at night. We might never be able to probe beyond the Planck scale. Not because we lack technology, but because the universe itself prevents it. To create Planck-scale energies in a particle accelerator, you'd need to concentrate so much energy in one place that it would collapse into a black hole. The act of observing Planck-scale physics creates conditions that make observation impossible. It's a fundamental barrier encoded in the structure of space-time. This means there are aspects of reality we can never experimentally verify. The quantum structure of space-time at the Planck scale. The behavior of matter at trans-Planckian energies. The nature of singularities. These things might be forever beyond the boundaries of scientific investigation. Not because we're not clever enough, but because the universe has built-in limits that prevent us from accessing certain regimes of physics. And those limits might not be random. They might be protective. Think about what happens when you try to probe the Planck scale. You create black holes. You generate conditions where causality breaks down. You risk triggering vacuum decay or creating stable strangelets that could convert all matter to a new form. The boundaries might exist to prevent us from destroying ourselves through our own experiments. The universe might be structured so that certain knowledge is permanently inaccessible because accessing it would be fatal. This is not just philosophical speculation. There are serious calculations suggesting that sufficiently advanced civilizations could pose existential risks to themselves by probing fundamental physics too deeply. Creating a black hole is one thing. Creating a false vacuum bubble, or a strangelet seed, or a region where physical laws break down catastrophically is another. The boundaries of physical law might be protection mechanisms that keep the universe stable by preventing intelligent species from accidentally breaking reality. But let's go deeper. Because there's another type of boundary that we haven't discussed, and it might be the most important one. I'm talking about the boundary between existence and non-existence. The edge where being meets non-being. This isn't metaphysics. It's quantum field theory. In quantum mechanics, the vacuum isn't empty. It's a seething foam of virtual particles that pop in and out of existence on timescales so short they don't violate energy conservation. These particles exist at the boundary between being and non-being. They're real enough to have measurable effects. The Casimir force, the Lamb shift, Hawking radiation. All of these phenomena arise from vacuum fluctuations, from particles that exist at the edge of reality. But here's what recent experiments have shown. The boundary between virtual and real particles is permeable. Under certain conditions, virtual particles can become real. The Schwinger effect predicts that sufficiently strong electric fields can rip virtual particle pairs apart, preventing them from annihilating and forcing them into permanent existence. The energy of the field pays the cost of creating real matter from the vacuum. This has been verified experimentally. We can create something from nothing if we apply enough energy in the right way. This means the vacuum is not the lowest energy state. It's a metastable state sitting at the boundary between different configurations of reality. And that boundary can be crossed. With enough energy, you can transition from the vacuum to states with real particles. With even more energy, you might transition to entirely different vacuum states where the laws of physics change. The vacuum boundary is not fixed. It's a dynamic interface that responds to conditions in space-time. And this boundary might be eroding. Some models of dark energy suggest that the accelerating expansion of the universe is driven by slow decay of the vacuum state. The boundary between our vacuum and lower energy configurations might be gradually shifting, with implications for the ultimate fate of everything. If the boundary crosses completely, we'd experience vacuum decay, the catastrophic phase transition I mentioned earlier. Reality would be fundamentally restructured as the vacuum transitions to a lower energy state. But there's something even stranger about the vacuum boundary. It might not be smooth. Recent work in quantum field theory suggests the boundary between existence and non-existence has structure. It's not a clean interface but a fractal edge with complexity at all scales. Zoom in on the boundary and you find more complexity. Virtual particles that exist for different durations. Quantum fluctuations that create temporary structures in the vacuum. The boundary is alive with activity, churning and fluctuating in ways we're only beginning to understand. This fractal boundary might be where the laws of physics are generated. Instead of thinking of physical laws as eternal rules imposed from outside reality, they might be emergent properties of the vacuum boundary. The interactions between virtual particles, the patterns in quantum fluctuations, the statistical properties of vacuum foam. All of this activity at the boundary between existence and non-existence could be generating the regularities we perceive as physical law. If this is true, then the laws of physics are not fundamental. They're emergent from deeper structure at the vacuum boundary. And that structure might vary. Different regions of space-time might have slightly different vacuum boundaries, leading to slightly different emergent laws. Physical constants might not be constant everywhere. They might vary as the vacuum boundary shifts and fluctuates. We might be living in a universe where the laws of physics have geography, with different regions operating under slightly different rules determined by local properties of the vacuum. There's observational evidence for this. The fine structure constant, which determines the strength of electromagnetic interactions, appears to have different values in different regions of the universe. The measurements are controversial and could be systematic errors. But if they're real, they suggest that physical laws vary across space. The boundaries of the vacuum state are not uniform. They have texture and variation that manifests as changes in the constants we thought were constant. And if physical laws can vary in space, they can vary in time. The vacuum boundary might be evolving as the universe expands and ages. The laws of physics today might be different from the laws that operated in the early universe or that will operate in the far future. We might be living through a specific epoch in cosmic history when physical laws have particular values. But those values will drift over cosmic timescales as the vacuum boundary evolves. This is deeply unsettling. It means nothing is truly permanent. Not space. Not time. Not even the laws that govern how reality operates. Everything exists at boundaries that shift and change. The universe is not a static structure with fixed properties. It's a dynamic system where boundaries move, evolve, interact, and occasionally catastrophically reconfigure. Now let me tell you about the temporal boundaries. We've talked about spatial edges, but time has boundaries too. And they're just as strange and just as limiting as the spatial ones. The most obvious temporal boundary is the Big Bang. 13.8 billion years ago, time began. Before that moment, the concept of before doesn't make sense. Time is a property of the universe, not a background in which the universe exists. There is no time before time starts. The Big Bang is a boundary in temporal structure, a beginning beyond which we cannot extend the past. But the Big Bang boundary might not be absolute. Some cosmological models suggest time could be cyclic. The universe could undergo repeated cycles of expansion and contraction, with each Big Bang followed by a big crunch that creates the next Big Bang. In these models, the Big Bang isn't the beginning of time, just a boundary between different epochs. Time might extend infinitely into the past through an endless series of cosmic cycles. Or time might be emergent. Recent work in quantum gravity suggests that time itself might arise from more fundamental timeless structures. At the quantum level, there might be no such thing as time. Only quantum states and relationships between them. Time emerges when you have many quantum systems interacting in particular ways. The flow of time, the progression from past to future, might be a macroscopic phenomenon that doesn't exist at the fundamental level. If time is emergent, then temporal boundaries are places where the emergence breaks down. The Big Bang might be a boundary where time stops being well-defined because the underlying quantum structure is too extreme for time to emerge properly. Similarly, the far future might have temporal boundaries where the universe becomes so dilute or so dominated by dark energy that time ceases to be a meaningful concept. There are other temporal boundaries scattered throughout space-time. The event horizons of black holes are boundaries in time as well as space. If you fall into a black hole, your future becomes someone else's space. The singularity at the center isn't just a point in space. It's a moment in your future, a temporal boundary you inevitably reach once you've crossed the event horizon. And at that boundary, time ends. Not in the sense that you die, but in the sense that time itself ceases to be defined. The singularity is a place where the concept of temporal progression breaks down. But here's what recent theoretical work suggests. Singularities might not be points. They might be surfaces. Extended boundaries in space-time where time transitions from one mode to another. When you hit a black hole singularity, you might not be destroyed. You might transition to a region where time works differently, where the arrow of time points in a new direction or where multiple time dimensions exist. This connects to an idea from string theory. Our universe might have only one time dimension, but other configurations could have multiple times. 2 time dimensions. 3. More. In those configurations, causality would work very differently. Events wouldn't be ordered in a single sequence from past to future. They'd exist in a web of temporal relationships where multiple futures and multiple pasts coexist. The boundaries of our universe might be interfaces where our single-time reality meets regions with different temporal dimensionality. Crossing such a boundary would be incomprehensible. Your consciousness evolved to experience one time dimension. One past, one present, one future flowing in sequence. If you somehow crossed into a region with two time dimensions, your experience would be, what? Impossible to imagine. Your thoughts require time to unfold in sequence. Memory requires a distinction between before and after. In a region with multiple times, these structures might not work. You might not be able to think at all. But there's an even stranger temporal boundary. The heat-death of the universe. In the far future, if dark energy continues to dominate, the universe will expand to the point where all matter has decayed, all stars have burned out, and all black holes have evaporated. What remains is a cold, empty space with no energy gradients, no structure, no change. This is maximum entropy. The thermal equilibrium state where nothing can happen because everything is the same everywhere. At heat death, time effectively stops. Not because time ceases to exist, but because there are no processes that define temporal progression. Time requires change. Cause must lead to effect. Past must differ from future. At maximum entropy, there is no change. Every moment is identical to every other moment. The arrow of time vanishes because there's no way to distinguish forward from backward. Time exists in some mathematical sense, but it has no operational meaning. No observer could experience it or measure it. This is a temporal boundary. The edge of time not because time ends, but because time becomes meaningless. And we're heading toward this boundary. The accelerating expansion is driving the universe toward heat death. The timeline is incomprehensibly long, 10 to 100 years or more. But it's finite. Time as we understand it has a limited duration. Beyond the heat-death boundary, temporal structure dissolves into timeless equilibrium. Unless there's a way to reset the clock. Some models suggest that quantum fluctuations in an empty universe could eventually, given enough time, create a new Big Bang. Random variations in quantum fields, occurring over timescales of 10-10-100 years or longer, could concentrate enough energy to nucleate a new expanding region of spacetime. The heat-death boundary might not be permanent. It might be a transition phase between cosmic epochs. But even if the universe can reset itself, that raises a disturbing question. How many times has this happened already? Could our Big Bang be just one in an infinite series? Could we be living in a cyclic cosmos that has been repeating forever, with no true beginning and no true end? Just an endless sequence of universes separated by temporal boundaries where entropy peaks and then resets? This is called eternal return, and it's philosophically terrifying. If the universe repeats infinitely, then everything that can happen will happen infinitely many times. Every possible configuration of matter. Every possible history. Every possible version of you. You've existed before. You'll exist again. An infinite number of times. With no first time and no last time. Just endless repetition at the boundaries between cosmic epochs. But there's no way to verify this. Each cycle erases the previous one. Information cannot cross the temporal boundary between universes. You can never know if this is the first Big Bang or the trillionth. The temporal boundaries isolate each cosmic epoch completely. History only extends back to our Big Bang. Beyond that boundary, even if other universes existed, they're as inaccessible as regions beyond our spatial boundaries. This multiplicity of boundaries, spatial and temporal, physical and mathematical, creates a picture of reality far more complex than the simple models we started with. The universe isn't a straightforward structure expanding from a singular beginning. It's a multifaceted system with boundaries at every scale. Operating through every mechanism, constraining every aspect of existence. And we've only discovered a fraction of them. Consider what we haven't found yet. There might be boundaries in the structure of matter itself. Limits to how massive a particle can be or how small. Boundaries in the spectrum of possible forces. Edges in the configuration space of quantum fields. Each of these would represent a different way reality is constrained, a different mechanism through which the possible is separated from the impossible. And these boundaries might interact. Spatial boundaries could affect temporal ones. Information limits could constrain topological possibilities. The vacuum boundary could influence how physical laws vary across space. The universe might be a tightly coupled system where every boundary affects every other, creating a web of constraints that determines what can exist and what can happen. We're just starting to map this web. Every new observation reveals new boundaries or new relationships between known ones. The James Webb Space Telescope has found patterns in the early universe that suggest additional boundary structures we hadn't predicted. Gravitational wave detectors are revealing how space-time responds to extreme conditions, providing insights into where geometric boundaries might lie. Particle accelerators continue to probe the edges of physical law, searching for the points where our theories break down. Each discovery makes the picture more complex, more beautiful, more terrifying. We thought we understood the shape of reality. We were wrong. Reality has more boundaries, more edges, more limits than we imagined. And each boundary we discover raises new questions. Why there? Why that form? Why those properties? The search for answers is driving physics into strange new territories. Theories involving higher dimensions, parallel universes, holographic principles, emergent spacetime. Each attempts to explain the boundaries we observe by embedding them in larger structures. But every explanation introduces new boundaries of its own. New edges to the theoretical frameworks. New limits to what the mathematics can describe. We might be approaching a boundary in knowledge itself. A point where human intelligence, even augmented by computers and artificial intelligence, simply cannot comprehend the structure of reality beyond a certain level of complexity. Our brains evolved to survive on African savannas. We can grasp quantum mechanics and general relativity, but only through enormous effort and heavy mathematical abstraction. The true nature of cosmic boundaries might be too complex, too abstract, too alien for minds like ours to fully grasp. But we keep trying. We keep pushing against the boundaries of knowledge, trying to understand the boundaries of existence. And occasionally, we succeed. We figure something out. We solve a problem. We map another edge of reality. The boundaries constrain us, but they don't stop us. We're bounded creatures studying boundaries, limited intelligences exploring limits. And somehow, improbably, we're making progress. That's the final message. The universe has boundaries everywhere. Edges, limits, constraints at every scale and through every mechanism. You exist within nested layers of boundaries that define what you are and what you can do. But within those constraints, you can still think, still question, still discover. The boundaries don't make you powerless. They make you focused. They give you something to push against, something to map and measure and understand. The universe ends. In space, in time, in physical law, in information capacity. In ways we've discovered and ways we haven't. But you don't end at those boundaries. Your understanding can extend right up to them. Your consciousness can grasp what the boundaries are even if you can't cross them. And that makes you remarkable. A bounded being who knows it's bounded. A finite creature who understands the infinite complexity of its own limitations. We were wrong about where the universe ends. It ends everywhere. In every direction, through every dimension, at every scale. The cosmos is nothing but boundaries. Nested and interlocked and interacting in ways we're still deciphering. And you're here, in the middle of it all, conscious and curious and capable of understanding what bounds you. That's not insignificance. That's the opposite. You're the universe becoming aware of its own edges. Reality studying its own limits. And there's nothing small about that at all. Now let me tell you about the boundaries nobody talks about. The ones that exist inside your head right now, reading these words. Consciousness has edges. Your awareness isn't infinite. You can only hold about 7 items in working memory at once. You can only pay attention to one stream of thought at a time, despite the illusion of multitasking. Your perception samples reality at roughly 40 Hz, creating a discontinuous experience that your brain stitches together into the illusion of continuous existence. These are cognitive boundaries. Hard limits on what your mind can process, remember, or experience. But here's what neuroscience is discovering. These boundaries aren't fixed features of biological hardware. They're dynamic interfaces that your brain actively constructs. The edges of your conscious experience are being generated right now by neuroprocesses that decide what enters awareness and what remains unconscious. You're not passively receiving reality. You're actively building a bounded model of it, and most of existence stays forever outside those boundaries. Consider your visual field. You think you see continuously in all directions, but you don't. Your eyes have a blind spot where the optic nerve connects to the retina. No photoreceptors exist there. You're literally blind in that region. Yet you never notice it because your brain fills in the missing information with predictions based on surrounding context. The boundary is invisible because your consciousness actively hides it from you. And it gets worse. Your peripheral vision is terrible. You have high-resolution color vision only in the central 2 degrees of your visual field. Everything else is blurry, low resolution, nearly monochrome. But it doesn't feel that way. Your brain constructs the experience of seeing clearly everywhere by rapidly moving your eyes and building a mental model from hundreds of quick glances. The rich, detailed visual world you experience is mostly fabricated. You're living inside a boundary that pretends to be boundless. This matters for understanding cosmic boundaries because every observation of the universe passes through the boundaries of human perception. We don't see the cosmos directly. We see instruments that measure radiation that traveled across space that we interpret through theories that exist as neural patterns within bounded consciousness. Layer upon layer of boundaries separate us from reality itself. The edges of the universe we've been discussing aren't just out there. They're in here, woven into the structure of how we know anything at all. And consciousness itself might have a boundary. A maximum amount of integrated information that can exist in a unified phenomenal experience. Giulio Tononi's integrated information theory proposes that consciousness is measured by phi, a quantity representing how much information is generated by a system beyond what its parts generate independently. Higher phi means more consciousness. But phi might have an upper limit determined by the physical constraints of information processing. If consciousness has a maximum phi, then there's a boundary to how aware anything can be. No matter how large a brain you build or how many neurons you connect, you eventually hit a ceiling. A limit to how much the universe can experience itself through conscious observers. We might be nowhere near that limit. Or we might be approaching it. Human consciousness might be close to the maximum phi that can exist in our region of space-time given the available energy and information capacity. This creates an observer boundary. A limit not on what exists, but on what can be observed. Even if the universe extends infinitely beyond all the boundaries we've discussed, consciousness might only be able to experience a finite subset. The maximum phi limit would constrain how much of reality any observer can comprehend. Regardless of their intelligence or technology, you could build a Jupiter-sized brain with more neurons than stars in the galaxy, and it still might hit the consciousness boundary before it hits the cosmic horizon. But there's another type of observer boundary that's even more restrictive. The Bekenstein bound doesn't just limit information storage. It limits computation. There's a maximum number of operations per second that can be performed in a given volume of space before it collapses into a black hole. This is called the Bremerman-Bekenstein limit, and it's approximately 10 to 51 operations per second per kilogram of matter. This means thinking has boundaries. Complex thoughts require many computational steps. Solving hard problems requires vast numbers of calculations. But physics limits how fast you can think regardless of how cleverly you arrange your hardware. You cannot build an infinitely fast computer because going too fast creates a black hole. The universe itself prevents unlimited computation through fundamental constraints on information processing. And it gets stranger. Seth Lloyd calculated the maximum number of operations the observable universe could have performed since the Big Bang. The answer is roughly 10 to 120 operations. That's a lot. That's more than enough for everything that's happened in cosmic history. But it's finite. The universe has only computed a limited number of states. It has only explored a finite region of its possibility space. This means there are thoughts that have never been thought, configurations of information that have never existed, mathematical proofs that haven't been discovered not because they're difficult but because there hasn't been enough computation time in the history of the universe to find them. We're living in a cosmos with a finite computational history, and that constrains what patterns can have emerged, what structures can have formed, what knowledge can have been generated. The computational boundary also affects the future. If the universe continues expanding and cooling, eventually there won't be enough free energy to perform computations. Stars will burn out. Black holes will evaporate. The background temperature will drop toward absolute zero. At some point, the energy required to flip a bit exceeds the energy available in any bounded region. Computation stops. Thought becomes impossible. This is another form of heat death, but focused specifically on information processing. Freeman Dyson calculated that advanced civilizations might survive heat death by slowing down their computation to match the available energy. Think slower and slower as the universe cools, stretching each thought over longer and longer periods. In principle, you could have infinite subjective time by thinking at ever-decreasing rates. But recent work suggests this doesn't work. Quantum mechanics introduces noise that accumulates over time. Error correction requires energy. Below a certain temperature, the energy cost of maintaining coherent information exceeds what's available. There's a minimum temperature for thought, and the universe will eventually cool below it. This creates an absolute computational boundary, a point in the far future where thinking becomes thermodynamically impossible. Not difficult. Not expensive. Impossible. No matter how clever you are, no matter what technology you develop, you cannot think when there's insufficient free energy to flip bits and correct errors. The universe will cross a threshold beyond which consciousness cannot exist in any form. And we can calculate when this happens. Depending on the model of dark energy and the expansion rate, the computational boundary appears somewhere between 10 to 100 and 10 to 1,000 years in the future. Those are incomprehensibly large numbers, but they're finite. Thought has a limited lifespan. Consciousness is a temporary phenomenon in cosmic history. There was a time before minds existed, and there will be a time after they're impossible. You exist in the narrow window between those boundaries. In the brief era when matter is organized enough for consciousness but the universe hasn't yet cooled to the point where thought becomes impossible. You're living at a special time, not because you're important, but because consciousness can only exist during specific epochs when thermodynamic conditions permit it. The boundaries of thought bracket your existence on both sides. But let's return to experimental reality. How do we actually search for these boundaries? What does it mean to hunt for the edge of the universe? Several experiments are underway right now that probe different boundaries in different ways. The Planck satellite mapped the cosmic microwave background with unprecedented precision, searching for signatures of topological boundaries or multiply connected space. If the universe loops back on itself, light from the Big Bang should show repeated patterns where photons have traveled around the cosmos multiple times. Planck found hints of such patterns, but nothing conclusive. The boundaries might be there, just beyond our current detection threshold. The Dark Energy Survey is mapping how cosmic structure evolved over billions of years, looking for changes that might indicate we're approaching conformal boundaries or vacuum phase transitions. If the vacuum state is metastable, there should be subtle variations in how dark energy behaves across space and time. DES has found some anomalies, regions where the expansion rate doesn't quite match predictions, but it's unclear if these are real boundaries or systematic errors. LIGO and other gravitational wave detectors are revealing how spacetime responds when black holes collide. These observations probe general relativity in extreme regimes where it might break down. So far, Einstein's theory holds up perfectly. But each new detection pushes closer to the boundaries of testability. Eventually, we might observe gravitational waves from conditions so extreme that general relativity fails to predict them accurately. That failure would mark a boundary in physical law. And then there's the quantum vacuum experiments. Teams at CERN and other facilities are trying to create conditions where the Schwinger effect produces real particles from the vacuum. They're literally trying to pull matter from nothing by applying intense electromagnetic fields. Success would demonstrate that the boundary between existence and non-existence is crossable. That something can emerge from nothing if you push hard enough. These experiments share a common feature. They're all pushing against boundaries, trying to find the edges of what's possible and what's knowable. Some will succeed. Some will fail. But each attempt reveals something about the structure of reality and where its limits lie. We're in an era of boundary exploration, systematically probing the edges of existence through observation and experiment. But here's the disturbing part. Every boundary we find raises the question of what lies beyond it. And that question might be fundamentally unanswerable. Not because we lack technology or intelligence, but because the boundaries themselves prevent us from accessing the information we need to answer. This creates what philosophers call epistemic boundaries, limits on knowledge that arise from the structure of reality rather than the limitations of observers. You can't know what's beyond the cosmic event horizon because signals from there can never reach you. You can't know what happens inside a black hole singularity because information can't escape. You can't know the exact quantum state of a system because measurement disturbs it. These aren't practical limitations. They're fundamental boundaries built into the laws of physics. And epistemic boundaries multiply. Imagine you want to know whether the universe is finite or infinite. If it's infinite, you can never verify that by observation because you can only see a finite region. If it's finite but much larger than the observable universe, you might never see enough to determine its true size. The observational boundaries prevent you from answering even basic questions about cosmic structure. You're trapped inside a bounded region trying to infer the properties of a much larger whole, and the boundaries ensure you'll never have complete information. This is the human condition in cosmological form. We're bounded beings with bounded knowledge trying to understand a reality that might extend infinitely beyond our boundaries. Every answer raises new questions. Every boundary we map reveals other boundaries beyond it. We peel back layers of ignorance only to find more layers underneath. The structure of knowledge itself has boundaries, and those boundaries might be irreducible. But despite all these constraints, we've made extraordinary progress. We've gone from thinking the Milky Way was the entire universe to understanding we're in one galaxy among trillions. We've discovered dark matter and dark energy. We've detected gravitational waves and photographed black holes. We've mapped the cosmic microwave background and calculated the age of the universe to within 1% accuracy. We've pushed our understanding right up to the boundaries of what's knowable. And that pushing continues. Right now, new telescopes are being built that will see farther and more clearly than ever before. The Nancy Grace Roman Space Telescope will survey vast regions of sky, mapping dark energy and searching for signatures of topological boundaries. The extremely large telescope will observe the first galaxies with enough detail to test our models of structure formation. Next-generation gravitational wave detectors will probe black hole mergers with sensitivity that might reveal quantum gravitational effects. Each new instrument pushes against the boundaries a little harder. and each pushes us closer to the ultimate question. What determines where the boundaries are? Why does the universe have the edges it does rather than some other configuration? This is where physics meets philosophy in the deepest way. The boundaries of the universe aren't arbitrary. They follow from physical laws, from the properties of spacetime, from quantum mechanics and thermodynamics and information theory. But those laws themselves have structure. They could have been different. Why these laws? Why these constants? Why this particular configuration of reality rather than some other? The anthropic principle provides one answer. The boundaries are where they are because those boundaries allow for the existence of observers like us. If the boundaries were significantly different, life couldn't exist, so we shouldn't be surprised to find ourselves in a universe with life-compatible boundaries. But this just pushes the question back. Why does the space of possible universes include configurations where observers can exist? Why anything rather than nothing? These questions might not have answers. They might lie beyond the ultimate boundary, the edge of rational explanation itself. There might be no reason why the universe has the properties it does. It might just be a brute fact, an arbitrary configuration with no deeper justification. Reality might bottom out in contingency, in choices or chances that have no explanation beyond. That's how it is. And you know what? That's okay. Not knowing the ultimate reason doesn't prevent us from mapping the structure. Not understanding why boundaries exist doesn't stop us from discovering where they are and how they work. We can study reality without having final answers about why reality exists at all. The boundaries constrain our knowledge, but they don't make knowledge impossible. They just make it finite. Which brings us to the final realization, the one that ties everything together. You are a boundary detector. That's what consciousness does. It finds edges. Your perception carves the continuous flow of sensory data into discrete objects with boundaries. Your cognition takes undefined possibility space and collapses it into specific thoughts with beginnings and endings. Your memory creates boundaries in time, distinguishing past from present from future. Your very existence as a coherent self requires maintaining a boundary between you and not you. The universe finding its boundaries through cosmology is just a scaled-up version of you finding yours through perception. Same process. Same fundamental operation. Taking the undifferentiated and imposing structure through the identification of edges. The cosmos is doing through science exactly what your brain does through consciousness. Defining itself by discovering what it is not. Understanding its nature by mapping where it ends. This makes the search for cosmic boundaries deeply personal. You're not studying something external to you. You're studying the same process that creates your experience of being you. The boundaries of the universe and the boundaries of your consciousness are reflections of the same underlying pattern. Reality organizing itself by finding its limits. Being defining itself through non-being. Existence understanding itself by discovering where existence stops. And here's the beautiful paradox at the heart of it all. Boundaries are limits. They constrain what can exist and what can be known. They fence us in and cut us off from vast regions of reality we can never access. But boundaries are also the source of all structure and meaning. Without edges, there are no shapes. Without limits, there are no forms. Without constraints, there are no possibilities because everything is everything and nothing is distinguishable from anything else. The boundaries don't diminish reality. They create it. The universe needs edges to be a universe rather than an undifferentiated void. You need boundaries to be you rather than dispersed chaos. Structure requires limits. Form requires constraints. Meaning requires that some things are and other things are not. So yes, we were wrong about where the universe ends. It doesn't end in one place or one way. It ends everywhere and always, through mechanisms operating at every scale from the quantum foam to the cosmic horizon. The boundaries are not exceptions to reality. They are reality. The universe is boundaries all the way down and all the way up. Nested limits that give form to existence and make structured being possible. And you are here, in the middle of infinite boundaries, conscious and curious and capable of understanding what bounds you. You exist because boundaries exist. You think because thought has limits. You perceive because consciousness has edges. You are a temporary knot of complexity maintained by boundaries that separate your patterns from the chaos outside them. And for a brief moment in cosmic history, those patterns include the knowledge of boundaries themselves. The universe began at a boundary 13.8 billion years ago. It will end at boundaries in the incomprehensibly distant future. Between those temporal limits, between the spatial edges and informational constraints and topological seams and all the other boundaries we've explored, there exists this moment. Right now. You, reading these words, understanding them, integrating them into your bounded consciousness. This is what it means to be human in a bounded universe. To exist temporarily within layers of constraints that define what you are and what you can do. To push against those boundaries through science and philosophy and art. To map the edges of reality even knowing you can never cross them. To understand the limits while living fully within them. The universe ends. It ends in space and time and physical law and information capacity and consciousness itself. It ends through mechanisms we understand and mechanisms we're still discovering and mechanisms we might never comprehend. But between all those endings, in the finite volume of space-time that's causally connected to you, there's room for beauty and complexity and understanding. There's space for you to exist and think and wonder about the boundaries that contain you. We were wrong about where the universe ends. But we were right to ask the question. And in asking, in searching, in pushing against the boundaries to see where they are and how they work, we've done something remarkable. We've taken a tiny fraction of the universe's matter, organized it into conscious observers, and used those observers to map the structure of the whole. We've made the cosmos aware of itself. We've turned boundaries into knowledge. That's not a defeat. That's not insignificance. That's the most improbable, most complex, most meaningful thing that matter can do. You are the universe bounding itself. Reality defining its limits. Existence discovering where existence stops. And in that discovery, in that boundary-finding process, the cosmos achieves something it cannot achieve through mere expansion or mere existence. It achieves understanding. It achieves meaning. Through you. Through minds like yours that can grasp the structure of reality even while trapped inside it. The boundaries don't trap you. They define the arena in which understanding becomes possible. They create the constraints against which consciousness can push and in pushing, discover what's real. The universe ends. But its ending gives it shape. And that shape, those boundaries, those limits that we've been mapping throughout this entire journey, they're not the enemy of existence. They're its foundation. They're what makes the universe something rather than nothing. They're what makes you rather than chaos. They're what makes any of this mean anything at all. So embrace the boundaries. Study them. Map them. Push against them. Not because you can overcome them, but because understanding them is understanding reality. The edges of the universe are the structure of being itself. And you, impossibly, improbably, temporarily, get to know them. Get to be the universe discovering where it ends. Get to participate in the cosmos understanding its own limits. We were wrong about where the universe ends. It ends everywhere. It ends in ways we're still discovering. It ends in forms that might remain forever beyond our grasp. But it ends. And that's not a flaw in reality. That's what makes reality real. That's what makes existence structured enough to support complexity and consciousness, and the remarkable fact that somewhere, in some bounded region of space-time, matter has organized itself into you. Into an observer who can read these words and grasp their meaning and understand, however briefly, the magnificent architecture of boundaries that defines where the universe ends and what that ending means. The universe is bounded. You are bounded. And within those bounds, we've discovered something precious. We've found that limits are not limitations. They're the structure that makes everything possible, including this moment, this understanding, This small but infinite realization that you exist at the edge of everything, mapping boundaries, knowing limits, and through that knowledge, achieving something the boundless never could. Meaning, purpose, understanding itself. The universe ends so that these can exist. So that you can exist. So that somewhere in the vastness of bounded reality, consciousness can emerge and ask where the universe ends and discover that the answer, impossible and beautiful, is everywhere and nowhere and right here, right now, in you.